Good morning, Year 12. It is Thursday morning and I'm re-recording all the stuff that I did yesterday because I forgot to turn the microphone back on. So we're doing 4 sketches this morning and we're using what we know about stationary points, points of inflection, concavity, as well as all the other tools we've learnt through the years to do 4 sketches. I'm going to break those up into 4 videos and this is going to be a long lesson. So we're going to have 3 days to get through these because there's so much to it. But this first page you've got in front of you is just reminding you of the tools you've got to help you work out what a curve looks like. And that is stationary points, where the first derivative is equal to 0, points of inflection, where the second derivative is equal to 0, and concavity changes. Okay, we can still find the intercepts, though we can't always find our x-intercepts. We can look at restrictions on the domain and range. We can look at asymptotes and what happens to our function as x approaches positive and negative infinity. And we can use what we know about a function's oddness. So oddness would be something like y equals x cubed, which has rotational symmetry. Evenness. So say y equals x squared minus 3 would be an even function. So we've got that axis of symmetry there. And we can still do that table of values. So an apology first. I haven't given you nearly enough space to do some of these questions and I've had to add pages in. So have some paper on standby because you're going to need it. There's a lot of work that goes into curve sketching, which is why you won't find a lot of them in an exam because they're so time consuming. All right, let's move on to our first one. So we've got f of x equals x cubed minus 3x squared minus 9x plus 1. And the question specifically asks you to find the stationary points and points of inflection and hence sketch the curve. So we know that our basic cubic is going to look like that. So we're expecting, because our leading coefficient, the number in front of the x cubed, is positive, it's going to be facing that way. So we're expecting to find a maximum, a minimum, and somewhere in between them, round about there, a point of inflection where we change from being concave down to concave up. All right, first step, let's differentiate. So we end up with 3x squared minus 6x minus 9. We find stationary points by putting the first derivative equal to 0. So I'm actually going to explicitly say that. Stationary points where f dash x equals 0. So 3x squared minus 6x minus 9. And the smart way to go about this is to divide throughout by 3 first. It will factorize if you don't, but it'll be much harder. So dividing throughout by 3, I get x squared minus 2x minus 3 equals 0. And that factorizes to x minus 3, x plus 1 equals 0. So x equals 3 or x equals minus 1. So the next step is to find the y values by substituting those x values back into the original function. Now I'm going to use my Desmos calculator, and what I'm going to do, because later on I want to be substituting some values in, I'm going to set up a little program. So Hamish, you can do this on your Casio. If you've got a Sharp 532, you can do it. So instead of putting x cubed minus 3x squared, I'm going to put a cubed minus 3 times, and I'll go back to get my a squared minus 9a and then plus 1. All right, so it's complaining because it doesn't know what a is, and that's fair enough. But I just wanted to put that in there to start. So now I'm going to assign a value. I'm going to say a equals 3. And when a equals 3, the value of my function is negative 26. So that's our possible turning point. So I'm going to change the value of a to negative 1, and when I do that I end up with y equals 6. So you can just go out of the way for the time being. So 3 minus 26 and negative 1, 6 are stationary points. So to determine the type of stationary points they are, we have two options. We can test using the first derivative and look at the changing gradient from positive to negative. But because this is a polynomial and easily differentiated, I'm going to use the second derivative and test concavity. So my second derivative, f double dash of x, I'm going to end up with 6x minus 6. So if I substitute 3 in there, so f double dash of 3, I'll get 6 lots of 3 minus 6, which is 12, which is importantly greater than 0. So greater than 0 tells me I'm dealing with something that is concave up, and so we've got 3 negative 26 is a minimum. So testing our other point, negative 1, f double dash of negative 1, 6 lots of negative 1 minus 6 gives us negative 12. And negative 12 is, of course, negative, which means that my curve is concave down at that point, showing we've got a maximum. So we need to actually explicitly state that. We need to say negative 1, 6 is a maximum, and that's what we were expecting based on our knowledge of what this curve looks like. And 3 negative 26 is a minimum. All right, our next step is to find that point of inflection, and we do that by setting our second derivative equal to 0 and checking that concavity changes on either side. So for points of inflection, f double dash of x equals 0, which gives me 6x minus 6 equals 0, which gives me x equals 1. So I'm just going to use my calculator again, And if I set the value of a to 1, I get negative 10. And so I've therefore got 1, negative 10 may be a point of inflection. I'm just going to abbreviate there. Right, in order to be sure, I need to test either side. So I need my little table of values, and I am testing the second derivative. I know when x is 1, the second derivative is 0. I want to test if concavity changes either side of that. So I'll test 0. So remember our second derivative is 6x minus 6. So when we substitute 0 in, it's negative. When we substitute 2 in, 6 times 2 is 12 minus 6, it is positive. Concavity changes, that means that we are dealing with a point of inflection. Alright, it's time to put it together, decide on a scale and sketch this. And apologies to my class, the scale on the graph that I gave you wasn't ideal. So I have given you, uploaded to Google Classroom some stuff that you can print out if you've got a printer. If you don't have a printer, I don't know what to say. Alright, let's put this all together and sketch it. So our minimum goes down to negative 26. So we need to include that. We don't need to go any higher than 6 on the vertical scale. I think I'm going to do this in 3s. So minus 6, minus 12, minus 18, minus 24, minus 30, and if we look at our x values, we've found our maximum at x equals negative 1. Our point of inflection was at x equals 1. We really could stretch that out a little bit. So there's my decision. So let's put these points on. So negative 1, 6 is a maximum. 1, negative 10 is our point of inflection. So round about there-ish. And 3, negative 26 is our minimum. All right, the other point that it's quite easy to work out is our y-intercept, because to find our y-intercept, we just put x equals 0 in our original function, and we end up with 1. All right, now just to get some extra points, I'm going to use my calculator. I'm going to do negative 2 and see what that gets me. So negative 2 gets me negative 1. Let's try negative 3. Negative 3 gets me negative 26. So that gets me a better idea of the shape of this curve. So I've done negative 3 giving me negative 26. I've done negative 2 getting me negative 1. Already done negative 1 and 0, and 1. So I think I might just put 2 in there and then be happy with those results. So 2 gets me negative 21. So I'd encourage you to get this Desmos calculator. Doing this is very handy. It is built into the Casio calculators and the higher models of the Sharps, and it's really handy when you're doing this sort of thing where you just want a few extra points. Okay, let's put those points in. I already have. Good for me. All right. There's my maximum, my y-intercept. My point of inflection should be pretty straight from there. Now we're starting to look concave up. There's my minimum. And we zoom back off. And that's it. A lot of work for that cubic. All right, I will see you